A black hole is defined as a region of spacetime from which gravity prevents anything, including light, from escaping. The theory of general relativity predicts that a sufficiently compact mass will deform spacetime to form a black hole. Around a black hole, there is a mathematically defined surface called an event horizon that marks the point of no return. The hole is called black because it absorbs all the light that hits the horizon, reflecting nothing, just like a perfect black body in thermodynamics. Quantum field theory in curved spacetime predicts that event horizons emit radiation, like a black body with a finite temperature. This temperature is inversely proportional to the mass of the black hole, making it difficult to observe this radiation for black holes of stellar mass, or greater. Objects whose gravity fields are too strong for light to escape were first considered in the 18th century by John Michell and Pierre-Simon Laplace. The first modern solution of general relativity that would characterize a black hole was found by Carl Schwarzschild in 1916, although its interpretation as a region of space from which nothing can escape was first published by David Finkelstein in 1958. Long considered a mathematical curiosity, it was during the 1960s that theoretical work showed black holes were a generic prediction of general relativity. The discovery of neutron stars sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. Black holes of stellar mass are expected to form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can continue to grow by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. There is general consensus that supermassive black holes exist in the centers of most galaxies. Despite its invisible interior, the presence of a black hole can be inferred through its interaction with other matter, and with electromagnetic radiation such as light. Matter falling onto a black hole can form an accretion disk heated by friction, forming some of the brightest objects in the universe. If there are other stars orbiting a black hole, their orbit can be used to determine its mass and location. Such observations can be used to exclude possible alternatives, such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems, and established that the core of the Milky Way contains a supermassive black hole of about 4.3 million solar masses. Simulation of gravitational lensing by a black hole, which distorts the image of a galaxy in the background. Larger animation. The idea of a body so massive that even light could not escape was first put forward by John Michell in a letter written to Henry Cavendish in 1783 of the Royal Society. If the semi-diameter of a sphere of the same density as the Sun were to exceed that of the Sun, in the proportion of 500 to 1, a body falling from an infinite height towards it would have acquired at its surface greater velocity than that of light, and consequently supposing light to be attracted by the same force in proportion to its vis inertiae with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. John Michell. In 1796, mathematician Pierre-Simon Laplace promoted the same idea in the first and second editions of his book Exposition du Système du Monde. It was removed from later editions. Such dark stars were largely ignored in the 19th century, since it was not understood how a massless wave such as light could be influenced by gravity. General relativity. In 1915, Albert Einstein developed his theory of general relativity, having earlier shown that gravity does influence light's motion. Only a few months later, Carl Schwarzschild found a solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently gave the same solution for the point mass, and wrote more extensively about its properties. This solution had a peculiar behavior at what is now called the Schwarzschild radius, where it became singular, meaning that some of the terms in the Einstein equations became infinite. The nature of this surface was not quite understood at the time. In 1924, Arthur Eddington showed that the singularity disappeared after a change of coordinates, see Eddington-Finkelstein coordinates, although it took until 1933 for Georges Lemaître to realize that this meant the singularity at the Schwarzschild radius was an unphysical coordinate singularity. In 1931, Subramanian Chandrasekhar calculated, using special relativity, that a non-rotating body of electron-degenerate matter, above a certain limiting mass, now called the Chandrasekhar limit, at 1.4 solar masses, has no stable solutions. His arguments were opposed by many of his contemporaries, like Eddington and Lev Landau, who argued that some yet unknown mechanism would stop the collapse. They were partly correct. The white dwarf, slightly more massive than the Chandrasekhar limit, will collapse into a neutron star, which is itself stable, because of the Pauli exclusion principle. But in 1939, Robert Oppenheimer and others predicted that neutron stars above approximately 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, would collapse into black holes, for the reasons presented by Chandrasekhar, and concluded that no law of physics was likely to intervene and stop at least some stars from collapsing to black holes. Oppenheimer and his co-authors interpreted the singularity at the boundary of the Schwarzschild radius, as indicating that this was the boundary of a bubble in which time stopped. This is a valid point of view for external observers, but not for infalling observers. Because of this property, the collapsed stars were called frozen stars, because an outside observer would see the surface of the star frozen in time at the instant where its collapse takes it inside the Schwarzschild radius. Golden Age. In 1958, David Finkelstein identified the Schwarzschild surface as an event horizon, a perfect unidirectional membrane. Causal influences can cross it in only one direction. This did not strictly contradict Oppenheimer's results, but extended them to include the point of view of infalling observers. Finkelstein's solution extended the Schwarzschild solution for the future of observers falling into a black hole. A complete extension had already been found by Martin Kruskal, who was urged to publish it. These results came at the beginning of the golden age of general relativity, which was marked by general relativity and black holes becoming mainstream subjects of research. This process was helped by the discovery of pulsars in 1967, which, by 1969, were shown to be rapidly rotating neutron stars. Until that time, neutron stars, like black holes, were regarded as just theoretical curiosities, but the discovery of pulsars showed their physical relevance and spurred a further interest in all types of compact objects that might be formed by gravitational collapse. In this period, more general black hole solutions were found. In 1963, Reuker found the exact solution for a rotating black hole. 2 years later, Esri Newman found the axisymmetric solution for a black hole that is both rotating and electrically charged. Through the work of Werner Israel, Brandon Carter, and David Robinson, the no-hair theorem emerged, stating that a stationary black hole solution is completely described by the 3 parameters of the Kerr-Newman metric: mass, angular momentum, and electric charge. At first, it was suspected that the strange features of the black hole solutions were pathological artifacts from the symmetry conditions imposed, and that the singularities would not appear in generic situations. This view was held in particular by Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, who tried to prove that no singularities appear in generic solutions. However, in the late 1960s, Roger Penrose and Stephen Hawking used global techniques to prove that singularities appear generically. Work by James Bardeen, Jacob Bekenstein, Carter, and Hawking in the early 1970s led to the formulation of black hole thermodynamics. These laws describe the behavior of a black hole in close analogy to the laws of thermodynamics by relating mass to energy, area to entropy, and surface gravity to temperature. The analogy was completed when Hawking, in 1974, showed that quantum field theory predicts that black holes should radiate like a black body with a temperature proportional to the surface gravity of the black hole. The first use of the term black hole in print was by journalist Anne Ewing in her article Black Holes in Space dated the 18th of January, 1964, which was a report on a meeting of the American Association for the Advancement of Science. John Wheeler used term black hole a lecture in 1967, leading some to credit him with coining the phrase. After Wheeler's use of the term, it was quickly adopted in general use. Properties and structure. The no-hair theorem states that, once it achieves a stable condition after formation, a black hole has only three independent physical properties: mass, charge, and angular momentum. Any two black holes that share the same values for these properties, or parameters, are indistinguishable according to classical, i.e. non-quantum, mechanics. These properties are special because they are visible from outside a black hole. For example, a charged black hole repels other like charges just like any other charged object. Similarly, the total mass inside a sphere containing a black hole can be found by using the gravitational analog of Gauss's law, the ADM mass, far away from the black hole. Likewise, the angular momentum can be measured from far away using frame dragging by the gravitomagnetic field. When an object falls into a black hole, any information about the shape of the object or distribution of charge on it is evenly distributed along the horizon of the black hole, and is lost to outside observers. The behavior of the horizon in this situation is a dissipative system that is closely analogous to that of a conductive stretchy membrane with friction and electrical resistance, the membrane paradigm. This is different from other field theories, like electromagnetism, which do not have any friction or resistivity at the microscopic level, because they are time reversible. Because a black hole eventually achieves a stable state with only three parameters, there is no way to avoid losing information about the initial conditions. The gravitational and electric fields of a black hole give very little information about what went in. The information that is lost includes every quantity that cannot be measured far away from the black hole horizon, including approximately conserved quantum numbers such as the total baryon number and lepton number. This behavior is so puzzling that it has been called the black hole information loss paradox. Physical properties. The simplest static black holes have mass, but neither electric charge nor angular momentum. These black holes are often referred to as Schwarzschild black holes after Karl Schwarzschild, who discovered this solution in 1916. According to Birkhoff's theorem, it is the only vacuum solution that is spherically symmetric. This means that there is no observable difference between the gravitational field of such a black hole and that of any other spherical object of the same mass. The popular notion of a black hole sucking in everything in its surroundings is therefore only correct near a black hole's horizon. Far away, the external gravitational field is identical to that of any other body of the same mass. Solutions describing more general black holes also exist. Charged black holes are described by the Reissner-Nordstrom metric, while the Kerr metric describes a rotating black hole. The most general stationary black hole solution known as the Kerr-Newman metric, which describes a black hole with both charge and angular momentum. While the mass of a black hole can take any positive value, the charge and angular momentum are constrained by the mass in Planck units. The total electric charge Q and the total angular momentum J are expected to satisfy. For a black hole of mass m, black holes saturating this inequality are called extremal. Solutions of Einstein's equations that violate this inequality exist, but they do not possess an event horizon. These solutions have so-called naked singularities that can be observed from the outside, and hence are deemed unphysical. The cosmic censorship hypothesis rules out the formation of such singularities when they are created through the gravitational collapse of realistic matter. This is supported by numerical simulations. Due to the relatively large strength of the electromagnetic force, black holes forming from the collapse of stars are expected to retain the nearly neutral charge of the star. Rotation, however, is expected to be a common feature of compact objects. The black hole candidate binary X-ray source GRS 1915 + 105 appears to have an angular momentum near the maximum allowed value, Black hole classifications: class mass size: supermassive black hole (105 1010 soon 0.001400 intermediate mass black hole (103 soon 103 km Earth stellar black hole 10 soon 30 km micro black hole up to moon up to 0.1 mm. Black holes are commonly classified according to their mass, independent of angular momentum J, or electric charge Q. The size of a black hole, as determined by the radius of the event horizon, or Schwarzschild radius, is roughly proportional to the mass m, through where RSH is the Schwarzschild radius and m soon is the mass of the Sun. This relation is exact only for black holes with zero charge and angular momentum. For more general black holes it can differ up to a factor of 2. Event horizon. Event horizon: far away from the black hole, a particle can move in any direction, as illustrated by the set of arrows. It is only restricted by the speed of light. Closer to the black hole, spacetime starts to deform. There are more paths going towards the black hole than paths moving away. Note 1. Inside of the event horizon, all paths bring the particle closer to the center of the black hole. It is no longer possible for the particle to escape. The defining feature of a black hole is the appearance of an event horizon, a boundary in spacetime through which matter and light can only pass inward towards the mass of the black hole. Nothing, not even light, can escape from inside the event horizon. The event horizon is referred to as such, because if an event occurs within the boundary, information from that event cannot reach an outside observer, making it impossible to determine if such an event occurred. As predicted by general relativity, the presence of a mass deforms space-time in such a way that the paths taken by particles bend towards the mass. At the event horizon of a black hole, this deformation becomes so strong that there are no paths that lead away from the black hole. To a distant observer, clocks near a black hole appear to tick more slowly than those further away from the black hole. Due to this effect, known as gravitational time dilation, an object falling into a black hole appears to slow down as it approaches the event horizon, taking an infinite time to reach it. At the same time, all processes on this object slow down for a fixed outside observer, causing emitted light to appear redder and dimmer, an effect known as gravitational redshift. Eventually, at a point just before it reaches the event horizon, the falling object becomes so dim that it can no longer be seen. On the other hand, an indestructible observer falling into a black hole does not notice any of these effects as he crosses the event horizon. According to his own clock, which appears to him to tick normally, he crosses the event horizon after a finite time without noting any singular behavior. In particular, he is unable to determine exactly when he crosses it, as it is impossible to determine the location of the event horizon from local observations. The shape of the event horizon of a black hole is always approximately spherical. Note 2. For non-rotating, static black holes the geometry is precisely spherical, while for rotating black holes the sphere is somewhat oblate. Singularity. At the center of a black hole, as described by general relativity, lies the gravitational singularity, a region where the space-time curvature becomes infinite. For a non-rotating black hole, this region takes the shape of a single point, and for a rotating black hole, it is smeared out to form a ring singularity lying in the plane of rotation. In both cases, the singular region has zero volume. It can also be shown that the singular region contains all the mass of the black hole solution. The singular region can thus be thought of as having infinite density. Observers falling into a Schwarzschild black hole, i.e., non-rotating and not charged, cannot avoid being carried into the singularity once they cross the event horizon. They can prolong the experience by accelerating away to slow their descent, but only up to a point. After attaining a certain ideal velocity, it is best to free fall the rest of the way. When they reach the singularity, they are crushed to infinite density, and their mass is added to the total of the black hole. Before that happens, they will have been torn apart by the growing tidal forces in a process sometimes referred to as spaghettification, or the noodle effect. In the case of a charged Reissner-Nordstrom or rotating Kerr black hole, it is possible to avoid the singularity. Extending these solutions as far as possible reveals the hypothetical possibility of exiting the black hole into a different spacetime with the black hole acting as a wormhole. The possibility of traveling to another universe is, however, only theoretical, since any perturbation will destroy this possibility. It also appears to be possible to follow closed time-like curves, going back to one's own past, around the Kerr singularity, which lead to problems with causality, like the grandfather paradox. It is expected that none of these peculiar effects would survive in a proper quantum treatment of rotating and charged black holes. The appearance of singularities in general relativity is commonly perceived as signaling the breakdown of the theory. This breakdown, however, is expected. It occurs in a situation where quantum effects should describe these actions due to the extremely high density and therefore particle interactions. To date, it has not been possible to combine quantum and gravitational effects into a single theory, although there exist attempts to formulate such a theory of quantum gravity. It is generally expected that such a theory will not feature any singularities. Photon sphere. The photon sphere is a spherical boundary of zero thickness such that photons moving along tangents to the sphere will be trapped in a circular orbit. For non-rotating black holes, the photon sphere has a radius 1.5 times the Schwarzschild radius. The orbits are dynamically unstable. Hence any small perturbation, such as a particle of infalling matter, will grow over time, either setting it on an outward trajectory escaping the black hole, or on an inward spiral eventually crossing the event horizon. While light can still escape from inside the photon sphere, any light that crosses the photon sphere on an inbound trajectory will be captured by the black hole. Hence any light reaching an outside observer from inside the photon sphere must have been emitted by objects inside the photon sphere, but still outside of the event horizon. Other compact objects, such as neutron stars, can also have photon spheres. This follows from the fact that the gravitational field of an object does not depend on its actual size. Hence any object that is smaller than 1.5 times the Schwarzschild radius corresponding to its mass will indeed have a photon sphere. Ergo Sphere. The Ergo Sphere is an oblate spheroid region outside of the event horizon, where objects cannot remain stationary. Rotating black holes are surrounded by a region of space-time in which it is impossible to stand still, called the Ergo Sphere. This is the result of a process known as frame dragging. General relativity predicts that any rotating mass will tend to slightly drag along the space-time immediately surrounding it. Any object near the rotating mass will tend to start moving in the direction of rotation. For a rotating black hole, this effect becomes so strong near the event horizon that an object would have to move faster than the speed of light in the opposite direction to just stand still. The ergosphere of a black hole is bounded by the outer event horizon on the inside and an oblate spheroid, which coincides with the event horizon at the poles and is noticeably wider around the equator. The outer boundary is sometimes called the ergo surface. Objects and radiation can escape normally from the ergosphere. Through the Penrose process, objects can emerge from the ergosphere with more energy than they entered. This energy is taken from the rotational energy of the black hole, causing it to slow down. Formation and evolution. Considering the exotic nature of black holes, it may be natural to question if such bizarre objects could exist in nature, or to suggest that they are merely pathological solutions to Einstein's equations. Einstein himself wrongly thought that black holes would not form, because he held that the angular momentum of collapsing particles would stabilize their motion at some radius. This led the general relativity community to dismiss all results to the contrary for many years. However, a minority of relativists continued to contend that black holes were physical objects. And by the end of the 1960s, they had persuaded the majority of researchers in the field that there is no obstacle to forming an event horizon. Once an event horizon forms, Penrose proved that a singularity will form somewhere inside it. Shortly afterwards, Hawking showed that many cosmological solutions describing the Big Bang have singularities without scalar fields or other exotic matter. See Penrose-Hawking singularity theorems. The Kerr solution, the no-hair theorem, and the laws of black hole thermodynamics showed that the physical properties of black holes were simple and comprehensible, making them respectable subjects for research. The primary formation process for black holes is expected to be the gravitational collapse of heavy objects such as stars, but there are also more exotic processes that can lead to the production of black holes. Gravitational collapse. Gravitational collapse occurs when an object's internal pressure is insufficient to resist the object's own gravity. For stars, this usually occurs either because a star has too little fuel left to maintain its temperature through stellar nucleosynthesis, or because a star that would have been stable receives extra matter in a way that does not raise its core temperature. In either case, the star's temperature is no longer high enough to prevent it from collapsing under its own weight. The collapse may be stopped by the degeneracy pressure of the star's constituents, condensing the matter in an exotic denser state. The result is one of the various types of compact star. The type of compact star formed depends on the mass of the remnant, the matter left over after the outer layers have been blown away, such from a supernova explosion, or by pulsations leading to a planetary nebula. Note that this mass can be substantially less than the original star remnants. Exceeding 5 solar masses are produced by stars that were over 20 solar masses before the collapse. If the mass of the remnant exceeds about 3/4 solar masses, the Tolman-Oppenheimer-Volkoff limit, either because the original star was very heavy, or because the remnant collected additional mass through accretion of matter, even the degeneracy pressure of neutrons is insufficient to stop the collapse. No known mechanism, except possibly quark degeneracy pressure, see quark star, is powerful enough to stop the implosion, and the object will inevitably collapse to form a black hole. The gravitational collapse of heavy stars is assumed to be responsible for the formation of stellar mass black holes. Star formation in the early universe may have resulted in very massive stars, which upon their collapse would have produced black holes of up to 103 solar masses. These black holes could be the seeds of the supermassive black holes found in the centers of most galaxies. While most of the energy released during gravitational collapse is emitted very quickly, an outside observer does not actually see the end of this process. Even though the collapse takes a finite amount of time from the reference frame of infalling matter, a distant observer sees the infalling material slow and halt just above the event horizon, due to gravitational time dilation. Light from the collapsing material takes longer and longer to reach the observer, with the light emitted just before the event horizon forms delayed an infinite amount of time. Thus the external observer never sees the formation of the event horizon. Instead, the collapsing material seems to become dimmer and increasingly redshifted, eventually fading away. Primordial black holes in the Big Bang. Gravitational collapse requires great density. In the current epoch of the universe, these high densities are only found in stars, but in the early universe shortly after the Big Bang, densities were much greater, possibly allowing for the creation of black holes. The high density alone is not enough to allow the formation of black holes, since a uniform mass distribution will not allow the mass to bunch up. In order for primordial black holes to form in such a dense medium, there must be initial density perturbations that can then grow under their own gravity. Different models for the early universe vary widely in their predictions of the size of these perturbations. Various models predict the creation of black holes ranging from a Planck mass to hundreds of thousands of solar masses. Primordial black holes could thus account for the creation of any type of black hole. High-energy collisions. A simulated event in the CMS detector, a collision in which a micro-black hole may be created. Gravitational collapse is not the only process that could create black holes. In principle, black holes could be formed in high-energy collisions that achieve sufficient density. As of 2002, no such events have been detected, either directly or indirectly, as a deficiency of the mass balance in particle accelerator experiments. This suggests that there must be a lower limit for the mass of black holes. Theoretically, this boundary is expected to lie around the Planck mass. MP equals C/G 1.2 1019 GeV/C2 2.218 kilograms, where quantum effects are expected to invalidate the predictions of general relativity. This would put the creation of black holes firmly out of reach of any high-energy process occurring on or near the Earth. However, certain developments in quantum gravity suggest that the Planck mass could be much lower. Some brane-world scenarios, for example, put the boundary as low as 1 TeV/C2. This would make it conceivable for micro-black holes to be created in the high-energy collisions occurring when cosmic rays hit the Earth's atmosphere, or possibly in the New Large Hadron Collider at CERN. Yet these theories are very speculative, and the creation of black holes in these processes is deemed unlikely by many specialists. Even if micro-black holes should be formed in these collisions, it is expected that they would evaporate in about 10-25 seconds, posing no threat to the Earth. Growth. Once a black hole has formed, it can continue to grow by absorbing additional matter. Any black hole will continually absorb gas and interstellar dust from its direct surroundings and omnipresent cosmic background radiation. This is the primary process through which supermassive black holes seem to have grown. A similar process has been suggested for the formation of intermediate mass black holes in globular clusters. Another possibility is for a black hole to merge with other objects such as stars or even other black holes. Although not necessary for growth, this is thought to have been important, especially for the early development of supermassive black holes, which could have formed from the coagulation of many smaller objects. The process has also been proposed as the origin of some intermediate mass black holes. Evaporation. In 1974, Hawking showed that black holes are not entirely black, but emit small amounts of thermal radiation, an effect that has become known as Hawking radiation. By applying quantum field theory to a static black hole background, he determined that a black hole should emit particles in a perfect black body spectrum. Since Hawking's publication, many others have verified the result through various approaches. If Hawking's theory of black hole radiation is correct, then black holes are expected to shrink and evaporate over time because they lose mass by the emission of photons and other particles. The temperature of this thermal spectrum, Hawking temperature, is proportional to the surface gravity of the black hole, which, for a Schwarzschild black hole, is inversely proportional to the mass. Hence, large black holes emit less radiation than small black holes. A stellar black hole of 1 solar mass has a Hawking temperature of about 100 nanokelvins. This is far less than the 2.7 K temperature of the cosmic microwave background radiation. Stellar mass or larger black holes receive more mass from the cosmic microwave background than they emit through Hawking radiation, and thus will grow instead of shrink. To have a Hawking temperature larger than 2.7 K and be able to evaporate, a black hole needs to have less mass than the Moon. Such a black hole would have a diameter of less than 1/10 of a millimeter 87. If a black hole is very small, the radiation effects are expected to become very strong. Even a black hole that is heavy compared to a human would evaporate in an instant. A black hole the weight of a car would have a diameter of about 1024 m and take a nanosecond to evaporate, during which time it would briefly have a luminosity more than 200 times that of the Sun. Lower mass black holes are expected to evaporate even faster. For example, a black hole of mass 1 TeV/C2 would take less than 1088 seconds to evaporate completely. For such a small black hole, quantum gravitation effects are expected to play an important role, and could even, although current developments in quantum gravity do not indicate so, hypothetically make such a small black hole stable. Observational evidence. Images of gas cloud being ripped apart by the black hole at the center of the Milky Way. By their very nature, black holes do not directly emit any signals other than the hypothetical Hawking radiation, since the Hawking radiation, for an astrophysical black hole, is predicted to be very weak. This makes it impossible to directly detect astrophysical black holes from the Earth. A possible exception to the Hawking radiation being weak is the last stage of the evaporation of light. Primordial black holes. Searches for such flashes in the past have proven unsuccessful and provide stringent limits on the possibility of existence of light primordial black holes. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, will continue the search for these flashes. Astrophysicists searching for black holes thus have to rely on indirect observations. A black hole's existence can sometimes be inferred by observing its gravitational interactions with its surroundings. A project run by MIT's Haystack Observatory is attempting to observe the event horizon of a black hole directly. Initial results are encouraging. Accretion of matter. A computer simulation of a star being consumed by a black hole. The blue dot indicates the location of the black hole. Due to conservation of angular momentum, gas falling into the gravitational well created by a massive object will typically form a disk-like structure around the object. Friction within the disk causes angular momentum to be transported outward, allowing matter to fall further inward, releasing potential energy and increasing the temperature of the gas. In the case of compact objects such as white dwarfs, neutron stars, and black holes, the gas in the inner regions becomes so hot that it will emit vast amounts of radiation, mainly X-rays, which may be detected by telescopes. This process of accretion is one of the most efficient energy-producing processes known. Up to 40% of the rest mass of the accreted material can be emitted in radiation. In nuclear fusion, only about 0.7% of the rest mass will be emitted as energy. In many cases, accretion disks are accompanied by relativistic jets emitted along the poles, which carry away much of the energy. The mechanism for the creation of these jets is currently not well understood. As such, many of the universe's more energetic phenomena have been attributed to the accretion of matter on black holes. In particular, active galactic nuclei and quasars are believed to be the accretion disks of supermassive black holes. Similarly, X-ray binaries are generally accepted to be binary star systems in which one of the two stars is a compact object accreting matter from its companion. It has also been suggested that some ultraluminous X-ray sources may be the accretion disks of intermediate mass black holes. X-ray binaries. X-ray binaries are binary star systems that are luminous in the X-ray part of the spectrum. These X-ray emissions are generally thought to be caused by one of the component stars being a compact object accreting matter from the other, regular, star. The presence of an ordinary star in such a system provides a unique opportunity for studying the central object and determining if it might be a black hole. If such a system emits signals that can be directly traced back to the compact object, it cannot be a black hole. The absence of such a signal does, however, not exclude the possibility that the compact object is a neutron star. By studying the companion star, it is often possible to obtain the orbital parameters of the system and obtain an estimate for the mass of the compact object. If this is much larger than the Tolman-Oppenheimer-Volkoff limit, that is, the maximum mass a neutron star can have before collapsing, then the object cannot be a neutron star, and is generally expected to be a black hole. This animation compares the X-ray heartbeats of GRS 1915 and IGRJ 17091, two black holes that ingest gas from companion stars. The first strong candidate for a black hole, Cygnus X1, was discovered in this way by Charles Thomas Bolton, Louise Webster, and Paul Merton in 1972. Some doubt, however, remained due to the uncertainties resultant from the companion star being much heavier than the candidate black hole. Currently, better candidates for black holes are found in a class of X-ray binaries called soft X-ray transients. In this class of system, the companion star is relatively low mass, allowing for more accurate estimates in the black hole mass. Moreover, these systems are only active in X-ray for several months, once every 10-50 years. During the period of low X-ray emission, called quiescence, the accretion disk is extremely faint, allowing for detailed observation of the companion star during this period. One of the best such candidates is V404 Kg. quiescence and advection-dominated accretion flow. The faintness of the accretion disk during quiescence is suspected to be caused by the flow entering a mode called an advection-dominated accretion flow, ADAF. In this mode, almost all the energy generated by friction in the disk is swept along with the flow instead of radiated away. If this model is correct, then it forms strong qualitative evidence for the presence of an event horizon. Because, if the object at the center of the disk has a solid surface, it would emit large amounts of radiation as the highly energetic gas hits the surface, an effect that is observed for neutron stars in a similar state. Quasi-periodic oscillations. The X-ray emission from accretion disks sometimes flickers at certain frequencies. These signals are called quasi-periodic oscillations, and are thought to be caused by material moving along the inner edge of the accretion disk, the innermost stable circular orbit. As such, their frequency is linked to the mass of the compact object. They can thus be used as an alternative way to determine the mass of potential black holes. Galactic nuclei. Astronomers use the term active galaxy to describe galaxies with unusual characteristics, such as unusual spectral line emission and very strong radio emission. Theoretical and observational studies have shown that the activity in these active galactic nuclei, AGN, may be explained by the presence of supermassive black holes. The models of these AGN consist of a central black hole that may be millions or billions of times more massive than the Sun, a disk of gas and dust called an accretion disk, and two jets that are perpendicular to the accretion disk. Although supermassive black holes are expected to be found in most AGN, only some galaxies' nuclei have been more carefully studied in attempts to both identify and measure the actual masses of the central supermassive black hole candidates. Some of the most notable galaxies with supermassive black hole candidates include the Andromeda Galaxy, N32, M87, NGC 3115, NGC 3377, NGC 4258, NGC 4889, NGC 1277, OJ 287, APM 08279, plus 5255, and the Sombrero Galaxy. It is now widely accepted that the center of nearly every galaxy, not just active ones, contains a supermassive black hole. The close observational correlation between the mass of this hole and the velocity dispersion of the host galaxy's bulge, known as the M-sigma relation, strongly suggests a connection between the formation of the black hole and the galaxy itself. Simulation of gas cloud after close approach to the black hole at the center of the Milky Way. Currently, the best evidence for a supermassive black hole comes from studying the proper motion of stars near the center of our own Milky Way. Since 1995, astronomers have tracked the motion of 90 stars in a region called Sagittarius A star. By fitting their motion to Keplerian orbits, they were able to infer in 1998 that 2.6 million solar masses must be contained in a volume with a radius of 0.02 light-years. Since then, one of the stars, called S2, has completed a full orbit. From the orbital data, they were able to place better constraints on the mass and size of the object causing the orbital motion of stars in the Sagittarius A star region, finding that there is a spherical mass of 4.3 million solar masses contained within a radius of less than 0.002 light-years. While this is more than 3,000 times the Schwarzschild radius corresponding to that mass, it is at least consistent with the central object being a supermassive black hole, and no realistic cluster of stars is physically tenable. Effects of strong gravity. Another way that the black hole nature of an object may be tested in the future is through observation of effects caused by strong gravity in their vicinity. One such effect is gravitational lensing. The deformation of spacetime around a massive object causes light rays to be deflected, much like light passing through an optic lens. Observations have been made of weak gravitational lensing, in which light rays are deflected by only a few arcseconds. However, it has never been directly observed for a black hole. One possibility for observing gravitational lensing by a black hole would be to observe stars in orbit around the black hole. There are several candidates for such an observation in orbit around Sagittarius A star. Another option would be the direct observation of gravitational waves produced by an object falling into a black hole, for example a compact object falling into a supermassive black hole through an extreme mass ratio and spiral. Matching the observed waveform to the predictions of general relativity would allow precision measurements of the mass and angular momentum of the central object, while at the same time testing general relativity. These types of events are a primary target for the proposed laser interferometer space antenna. Alternatives. The evidence for stellar black holes strongly relies on the existence of an upper limit for the mass of a neutron star. The size of this limit heavily depends on the assumptions made about the properties of dense matter. New exotic phases of matter could push up this bound. A phase of free quarks at high density might allow the existence of dense quark stars, and some supersymmetric models predict the existence of Q stars. Some extensions of the Standard Model posit the existence of preons as fundamental building blocks of quarks and leptons, which could hypothetically form preon stars. These hypothetical models could potentially explain a number of observations of stellar black hole candidates. However, it can be shown from general arguments in general relativity that any such object will have a maximum mass. Since the average density of a black hole inside its Schwarzschild radius is inversely proportional to the square of its mass, supermassive black holes are much less dense than stellar black holes. The average density of a 108 solar mass black hole is comparable to that of water. Consequently, the physics of matter forming a supermassive black hole is much better understood, and the possible alternative explanations for supermassive black hole observations are much more mundane. For example, a supermassive black hole could be modeled by a large cluster of very dark objects. However, such alternatives are typically not stable enough to explain the supermassive black hole candidates. The evidence for stellar and supermassive black holes implies that in order for black holes not to form, general relativity must fail as a theory of gravity, perhaps due to the onset of quantum mechanical corrections. A much anticipated feature of a theory of quantum gravity is that it will not feature singularities or event horizons, and thus no black holes. In 2002, much attention has been drawn by the fuzzball model and string theory. Based on calculations in specific situations in string theory, the proposal suggests that generically the individual states of a black hole solution do not have an event horizon or singularity, but that for a classical/semi-classical observer the statistical average of such states does appear just like an ordinary black hole in general relativity. Open questions. Entropy and thermodynamics. The formula for the Bekenstein-Hawking entropy S of a black hole, which depends on the area of the black hole. A. The constants are the speed of light, c. the Boltzmann constant, k. Newton's constant, g. and the reduced Planck constant. In 1971, Hawking showed under general conditions Note 3, that the total area of the event horizons of any collection of classical black holes can never decrease, even if they collide and merge. This result, now known as the second law of black hole mechanics, is remarkably similar to the second law of thermodynamics, which states that the total entropy of a system can never decrease. As with classical objects at absolute zero temperature, it was assumed that black holes had zero entropy. If this were the case, the second law of thermodynamics would be violated by entropy-laden matter entering a black hole, resulting in a decrease of the total entropy of the universe. Therefore, Bekenstein proposed that a black hole should have an entropy, and that it should be proportional to its horizon area. The link with the laws of thermodynamics was further strengthened by Hawking's discovery that quantum field theory predicts that a black hole radiates blackbody radiation at a constant temperature. This seemingly causes a violation of the second law of black hole mechanics, since the radiation will carry away energy from the black hole, causing it to shrink. The radiation, however, also carries away entropy, and it can be proven under general assumptions that the sum of the entropy of the matter surrounding a black hole and 1/4 of the area of the horizon, as measured in Planck units, is in fact always increasing. This allows the formulation of the first law of black hole mechanics, as an analog of the first law of thermodynamics, with the mass acting as energy, the surface gravity as temperature, and the area as entropy. One puzzling feature is that the entropy of a black hole scales with its area rather than with its volume, since entropy is normally an extensive quantity that scales linearly with the volume of the system. This odd property led Gerard T. Hooft and Leonard Susskind to propose the holographic principle, which suggests that anything that happens in a volume of spacetime can be described by data on the boundary of that volume. Although general relativity can be used to perform a semi-classical calculation of black hole entropy, this situation is theoretically unsatisfying. In statistical mechanics, entropy is understood as counting the number of microscopic configurations of a system that have the same macroscopic qualities, such as mass, charge, pressure, etc. Without a satisfactory theory of quantum gravity, one cannot perform such a computation for black holes. Some progress has been made in various approaches to quantum gravity. In 1995, Andrew Strominger and Kamran Vafa showed that counting the microstates of a specific supersymmetric black hole in string theory reproduced the Bekenstein-Hawking entropy. Since then, similar results have been reported for different black holes both in string theory and in other approaches to quantum gravity, like loop quantum gravity. Information loss paradox. Because a black hole has only a few internal parameters, most of the information about the matter that went into forming the black hole is lost. Regardless of the type of matter which goes into a black hole, it appears that only information concerning the total mass, charge, and angular momentum are conserved. As long as black holes were thought to persist forever, this information loss is not that problematic, as the information can be thought of as existing inside the black hole, inaccessible from the outside. However, black holes slowly evaporate by emitting Hawking radiation. This radiation does not appear to carry any additional information about the matter that formed the black hole, meaning that this information appears to be gone forever. The question, whether information is truly lost in black holes, the black hole information paradox, has divided the theoretical physics community, see Thorne-Hawking-Prescott. In quantum mechanics, loss of information corresponds to the violation of vital property called unitarity, which has to do with the conservation of probability. It has been argued that loss of unitarity would also imply violation of conservation of energy. Over recent years, evidence has been building that indeed information and unitarity are preserved in a full quantum gravitational treatment of the problem.